Section 1.6, Applications of Linear Systems. In this section on applications of linear systems, in the lay textbook there are three different types of applications on which we're focused. One is outputs of various sectors in the economy, one is chemical reactions and their equations, and the third application is network flows. We're going to focus on the third one, and I'll leave it to you to peruse through the textbook to get a feel for the other two. So let's take a look at network flows. Network flows arise when you're studying the flow of one particular type of material through a network. This could be fluid flow, it could be traffic flows, it could be electrical current, it could be distribution of products from wholesalers to retailers. Any situation where you have junctions and you have things moving through a network grid controlled by those junctions, any type of situation like that, a network flow is appropriate. Network flows. What are the key ideas here? Well, for starters, when you look at a network, there are going to be two parts. There are going to be the junctions and the branches. The junctions are typically going to be represented by points or nodes, and the branches will be the connections among those nodes. We're going to get our equations as a result of the following key idea. The total flow into a network equals the total flow out of the network. And if we look at that on a smaller scale, the total flow into a single junction equals the total flow out of that junction. So the flow in equals the flow out. We're going to look at each junction in a network, and by equating the flow in to the flow out, we get an equation. Do that for multiple junctions, and you're going to get a system of equations. And based on the systems of equations that we've been studying throughout Chapter 1, you can probably guess where we're headed with this. Here's an example from the text that we will work out in detail here to give you a feel for how to solve a network flow problem. Intersections in England are often constructed as one-way roundabouts, such as the one shown in the figure. Now we've got the Brits driving on the left side of the street, so when they have their roundabout they are going to go around clockwise, compared to if you had one of these in Massachusetts or New Jersey or something like that, when you'd have it going counterclockwise. So we have a roundabout here, it's a one-way roundabout, and traffic in the circle is going around clockwise. In addition to the traffic that's going clockwise in the circle, for the junctions coming in and out of the circle, assume that traffic is flowing in the direction shown by the arrows. Find the general solution of the network flow. In addition, find the smallest possible value for x sub 6. Now when we say find the general solution of the network flow, what we're saying there is that it's not going to be a unique solution. It's not going to be the exact same number of cars on the road at all times. And that's not what we're going to have here, and that would be sort of an unrealistic model. What we're going to have is we're going to have some free variables, and then based on the free variables, the other variables in the system can be determined. And, based on that general solution that has free variables, we can kind of, by comparing the relationships among the variables, figure out the smallest value for x sub 6. Alright, so let's go to the next slide and actually start to work out some of these details. We're going to write equations that describe the flow in this network. We're going to get a system of equations by putting together one equation for each junction. And each equation is going to be of the form flow in equals flow out. The solution to the system of equations that we create by making these flow in equals flow out equations will give us the answer that describes the system flow. It's going to be a general solution that, typically there are going to be free variables, but it will give us a good idea of the relationship among the variables in the system. Okay, in the upper right-hand corner we have our diagram for the traffic flow through this roundabout. We have the traffic flowing in the directions indicated by the arrows. We have 6 junctions, and we have variables x sub 1 through x sub 6, so we're going to have 6 equations in 6 variables. And for each equation, it's going to be just a matter of calculating flow in, calculating flow out, and setting them equal to each other. So we're going to get our 6 equations in that way. Let's start with the equation for junction A. Now, if we look closely at junction A, we have one direction of traffic coming in and 2 directions of traffic going out. So what we're going to have there is, for the flow in, x sub 1 is the only traffic flow coming into that junction, and the 2 that are leaving junction A are 100 in one direction and x sub 2 in the other. So when we compare flow in to flow out, we're going to have that the flow in is x sub 1, and that's going to be equal to the flow out, which is 100 plus x sub 2. When we get to junction B, we have 2 directions of flow coming in, 50 and x sub 2, and the only flow out from junction B is x sub 3. So our equation is 50 plus x sub 2 equals x sub 3. For intersection C, we have x sub 3 coming in, and for the flow out, we have 120 in one direction and x sub 4 in the other direction, and together those make up the flow out. For junction D, we have 150 and x sub 4 coming in. We have x sub 5 flowing out. 2 more equations. The one for E, we have x sub 5 coming in, and 80 and x sub 6, that's a nice tongue twister, going out. And finally, for junction F, we have x sub 6 and 100 flowing in, and we have x sub 1 flowing out. So here are the 6 equations for this system. Now, these are not in standard form because you have constants on both sides, you have variables on both sides. The variables are not aligned. So in the next slide, we're going to start to work on simplifying the system, and the very first step will be just to get it in standard form. Okay, so our first job here is to get this system of 6 equations into standard form. So we'd like to have it so that on the left-hand side of the equation we have the variables in order, x sub 1, x sub 2, x sub 3, and so on. And then on the right-hand side we want to have the constant term. Our first equation here is going to be x sub 1 minus x sub 2 equals 100, which we could get by subtracting x sub 2 from both sides. For the second equation, we could also subtract x sub 2 from both sides, and we'd get negative x sub 2 plus x sub 3 equals 50. Continuing on in this way, we get our system of equations. What we're going to want to do in the upcoming slides is we're going to want to do things like get an augmented matrix that represents this system, and get it in an echelon form so that we can get a good feel for what the solution is. Okay, so here is the system of 6 equations that we just are carrying over from the previous slide, and we're going to make an augmented matrix, and we're going to try to achieve a solution for this system via the augmented matrix and its reduced echelon form. So let's make the augmented matrix and begin the row reduction process. For starters, we're going to have rows that consist mostly of zeros, ones, and negative ones until you get to that final column where we have the weights that are just in direct correspondence with the system. But to get this in echelon form, we'd like to have each row where its first non-zero entry is a 1. And so we have that for most of the rows except for the second row and the fourth row. So I'll multiply the second and fourth rows by negative 1 so that my leading non-zero entry in each row is a 1. And so here is the result of that process. In addition, we would like to have it so that for those leading non-zero entries in each row, the entries directly above them are zeros, and we have a lot of that, but as you can see here we have some negative 1s above those 1s that lead each row. So we're going to be doing some row reduction here. So let's go and try to row reduce this system of 6 equations, and it's really not that hard, and it actually gets easier as we go along here. So let's take a peek. Starting with this first row here. Now, how did I get this row? What I am doing to get this row here is I'm taking the first row and adding to it the second, third, fourth, and fifth rows. So I'm basically adding rows 1 through 5 here. Take that old matrix that was that you see in the bottom left here and add rows 1 through 5. And what that does is you can see that in the second, third, fourth, and fifth columns, when I add rows 1 through 5, there's exactly one 1 and one negative 1 that will cancel each other out, leaving just the 1 at the beginning and the negative 1 in the 6th entry of this new first row. So add rows 1 through 5 to get this row. Okay, to get the next row, add rows 2 through 5. And when we add rows 2 through 5, you're going to have sort of a similar sort of telescopic effect where in the middle you have 1s and negative 1s canceling each other out, with the end result here being this row 0, 1, 0, 0, 0, negative 1, 0. To get the new third row, in the old matrix, add rows 3 through 5. Add rows 3, 4, and 5, and you'll get this row here, which is 0, 0, 1, 0, 0, negative 1, 50. To get a new fourth row, add from the old matrix rows 4 and 5, and you'll get this. The fifth row is already in good shape, so just keep it the way it is. And now for the new sixth row, basically at this point what you're going to do is you could basically leave the sixth row the same, but then add the new sixth row and a negative of the new first row, and those are going to cancel each other out. So in the end here, you're eventually going to get a row of all zeros on the bottom, which you would kind of suspect for an equation here, or a system of equations with 6 variables, 6 unknowns, but likely a free variable. So in order to get that free variable here, in the row reduced form, there should be a row of all zeros. Okay, now we have a very nice reduced echelon form for this augmented matrix that represented our system of equations, and so from that we can basically read off the solution to this system in a very nice form. So let's start with the first equation there. That very first row of the augmented matrix is basically telling us that x sub 1 minus x sub 6 equals 100. And adding x sub 6 to both sides, you get that x sub 1 is going to be x sub 6 plus 100. Now note here, sort of a preview, if you look down to the 6th row of this augmented matrix, you're basically saying that x sub 6 is a free variable. So, and that's going to be your only free variable. So we're explaining the other 5 variables in terms of x6. So once we come up with a value for x sub 6, the free variable, the other values of the system will be predetermined. Alright, continuing on, the second row of the augmented matrix tells you that x sub 2 minus x sub 6 equals 0. So x sub 2 equals x sub 6. And continuing on with the next 3 rows, you're going to end up with x sub 3 equals x sub 6 plus 50. X sub 4 equals x sub 6 minus 70. And that's going to tell us something important about x sub 6, as we'll see in a moment. And then finally, x sub 5 equals x sub 6 plus 80. X sub 6 is going to be our free variable, as we noted a moment ago. And if we look at that fourth equation there, we're limited as to our values for x sub 6 because the flow through any one of these connections in our network has to be a positive flow when we're talking about, automobiles. So in order for x sub 4 to be a non-negative number, we need x sub 6 to be at least 70. So when we talk about the minimum value for x sub 6, the minimum value for x sub 6 is 70. Otherwise, you'd have negative automobile flow, which is not going to make any sense.